So regression it's very similar, more or less the same thing, except instead of predicting a class label, we're predicting a continuous value. So let's give an example of that. So suppose you're designing a system which is going to predict how much it's going to rain tomorrow, which is something we might find useful right now, right? And maybe you know the temperature, the atmospheric pressure, the location in latitude and longitude in the world, and all sorts of numbers that describe, your position. And we can create a function which will take that as data, as its input, and predict the number of centimeters of rain that we'll get, or millimeters or whatever. And that would be regression, right? So we're predicting as a function of some input variable, how much, some continuous value, an output variable. So these things are related, and they're functions in the mathematical sense of the term. So when you take like algebra, you learn about functions. A function is is a mathematical. It's hard to define it without even saying function, right? It's like something that takes in some variable, some input variable, one or more, x, y, z, and so on, and then gives you an output variable, which is dependent on the input variables. So this is a machine learning will do the same thing. We're creating a function, but the difference between this and the kind of functions that we're used to is that these are going to be learned by a computer, and we'll see kind of how they're structured to do that. And then another kind of task in machine learning that you'll find commonly is called clustering, which is this form of what's called unsupervised learning. So in unsupervised learning, there's no categories or labels at all. You're just taking unordered input data and clustering it, giving it sort of creating categories that they are distributed into, which we'll maybe do a bit of also. So let's describe neural networks, and what you're looking at is not a neural network. It's not even neurons. These are just I think myoblasts, which are made by a friend of mine who took some imagery. It's pretty cool. So these are actual neurons. We already talked about this, but we shouldn't take the analogy too far. But I do like to include these pictures because they're kind of beautiful. And we're going to describe what actual neurons look like, which is this, much less beautiful. So this is why I kind of like to start with this, to maybe just so you could be super disappointed when we see what they actually look like. So let's describe neural networks. The basic building block of a neural network is a neuron. Sometimes it's called an input, or sorry, sometimes it's called a node or a unit. There's lots of different synonyms, but we'll usually call them neurons. And a neuron is is basically like a cell which carries a value. It has a single value, a numeric value, a number. And the number which it carries is dependent on neurons which are sending their values to it. So this neuron, for example, is receiving values from 3 neurons, which it kind of sums together, and then it sends it outward to other neurons, right? Now, I'm going to show you an example of this, but before I do, let me actually, I think I have a better visual for this now. We just started working on this just yesterday, so this is kind of new. We're making our glossary, which is going to contain some of these in a little bit more detail. So you see that this is the visual that we were just looking at, and the actual value that this would carry, the neuron has what's called a bias term, which is another number. We'll call it B, right? But don't worry too much about what B is. When we get into training, I'll kind of give you an interpretation of it. But the value of this is calculated is actually really simple as far as like mathematically. It basically takes these 3 neurons which are feeding into it, and it sums them together with weights. So this is the formula that you should. Does everyone see this formula? Is that visible? I can make it bigger. All it is it takes these neurons, it sums them together, and it takes a weighted sum of them. So the weights are sort of associated with the connections themselves. So for example, if weight 1 is higher, then the value of our neuron is grows bigger with respect to x1. So it's kind of like weighing up evidence. You know, this neuron, you can think of it as a tiny classifier itself, which weighs up evidence from other neurons. So these neurons send it values, and it weighs them together, and it's a small function by itself. Now there's actually one more step, but let me, before I get to that, let's consider what we just see with this, right? So suppose the value that it sends is just this, z, we'll call it z, weighted sum. It's a function, right? Depending on what the weights are, the function has a different behavior, right? So you can think of this as a function of 3 variables. You can imagine it in sort of like a 3-dimensional space, and depending on what these weights are set to, the curvature of this function in space kind of changes. The way the relationship between its output variable and the input variables changes depending on these weights. That's a really important property because basically that's the central aspect of learning in machine learning. The learning means we're learning what these weights should be. Because if they're set one way, the neuron behaves in a certain way. If they're set another way, the neuron behaves in another way. And the question is, how do we find the behavior which fits the thing that we're trying to fit it to? Now, getting back to B, the bias term, this exists for mathematical reasons. We want to be able to sort of like, this is the y-intercept, right? When you learn in algebra, like the sort of place where it intersects where x equals 0. So it's like a translation term. It lets us move the function up and down. But really, when it comes to the learning part, this is more or less like another weight. So in learning, this has to be learned along with these other weights. It's like you can treat it like another weight. It's just another variable that we have to learn what the value of should be in order to make this neuron behave right. Now, I lied to you because I didn't mention it that one more step. Turns out it looks complicated, but it's not. So what happens is we get this value z, like we'll call it z, and then the value of y, like the value that this neuron carries, is there's actually one more step. We take this weighted sum, and then we run it through what's called an activation function. An activation function will map it to a new value, which is still proportional to the old value z. A typical one that used to be used a lot is called the sigmoid function, which is this. So that's 1 over 1 plus e to the negative z. You may look at this and be like, this seems horribly complicated. But all it is actually, let's see if I can get, let me get a visual of it. Sigmoid function just does this. It just takes something, takes some value, and it squashes it between 0 and 1. So this makes the behavior of the neuron such that it only outputs a value between 0 and 1. This turns out to be useful for reasons that are sort of beyond the scope of what we want to talk about. But there is an activation function. The reason why it's useful is that it makes it nonlinear. And when the function is nonlinear, it's more flexible, let's say. It's able to bend more. It's able to kind of represent a greater range of possible relationships between input and output variables. Sigmoid function is the sort of classical one. But it turns out that in practice, it's not usually used anymore. What's usually used is these days in machine learning are variants of what are called ReLU, which stands for rectified linear units. Sounds complicated, but all it is it just turns negative numbers into 0 and lets the rest pass through. So it's basically like whatever z is, if it's negative, make it 0. If it's positive, then let it pass unchanged. Which is also nonlinear. And for reasons that are beyond the scope of what we want to learn, ReLUs are kind of preferred. They seem to work better. experimentally. So that's a neuron by itself. So a neuron by itself is like a tiny classifier or a tiny function, right? It takes in whatever neurons are feeding it, and it is able to pass through an output. Now, this is basically a very small, simple one-layer neural network. It's composed of this, what we're looking at, like we're referring to this neuron, but this right here, this whole visual, is a one-layer neural network. It has 3 input variables and 1 output variable. And it's a tiny function, right? And you can see how it works. And depending on how we set the weight values, the curvature of this function changes. And the task of machine learning is to find the correct curvature. Something along those lines, right? In practice, we use bigger neural networks than this, though, and I'm going to show you that in the next slide. So a typical neural network might have more than one layer. So suppose we have a neural network that looks like this. We have two. This is called a 2-layer neural network. You might think it has 3, but we usually count layers that have connections going to them. So this is a 2-layer neural network because there's 2 layers of connections. It has 3 input neurons in the first layer, 2 layers in this middle layer, which is called a hidden layer. Hidden just means it's not an input or an output. So it's a hidden layer. And then there's 1 output neuron in the last layer. And all of the neurons in one layer connect to all of the neurons in the next layer. So this right here, like this neuron right here, if we just zoom in on it, is like what we just looked at in the last slide. It's a single, 3 neurons connect to it, right? But now, because there's multiple levels here of nonlinear activation units, the function has more flexibility than the single 1-layer neural network. It's able to represent more possible sort of modeling more possible behaviors. So let's do a tiny forward pass. A forward pass is what happens in a neural network is that we input some values. Let's say we get these values. I should warn you actually that the numbers are wrong. These are old images that I haven't fixed yet. So don't pay too much attention to numbers. Just kind of follow along the math symbolically. So we get some numbers here, right? And then we'll calculate each of these hidden neurons, which is again going to be this weighted sum, right? And then it gets this bias value, and then it goes through, in this case, a sigmoid. So this is what we get from these numbers, 0.46. We get negative 0.13. The reason why this is wrong is obviously, like I just told you, sigmoids are always between 0 and 1. And this is a negative number, so something's wrong with this visual. I screwed it up. Don't worry about that for now. So the number should be different. But the point is that both of these get this weighted sum of these other values. And then we do it again in the next layer. So this function mapped these 3 numbers, this input, to this output, right? And it should be trivial to see that if the weights had been different, then the output value would have been different. And it would have been different for any input that we get. So the idea with machine learning is that we can create a function which maps some input variables to some output variables, which is totally dependent on the way that we set the weights. And the key in machine learning is that we have to figure out what the right weights are, or what a good set of weights is, such that we get the kind of behavior that we want. So let's look at an example where this is like going to be a little bit more concrete. So I already mentioned this before. So we have this data set called MNIST, which is a data set of handwritten of images of handwritten digits. So these are all numbers that people handwrote, and we took images of them, which are 28 by 28 pixels big. So they're pretty small images. And we want to design a neural network which will look at these images and tell us what number is inside of them. right? So how would we do that, right? So for us, like if we look at this image of a 3, we take for granted how easy it is to recognize that. But to a computer, all of these pixels are numbers, right? So this 3 looks like this. So how do you go from all of this to this is a 3? Turns out that that's not so easy to do with a program that you write by hand, right? You can't just, you can imagine trying to create all sorts of, sort of like pseudo algorithms for figuring this out. Like, okay, if there's a lot of, if these numbers around here are kind of high and these ones here, it's hopeless, basically. It would be a really complicated program. And so the better way to do it would be to create a neural network which learns how to do it. And the way that you would do it is that you would create a neural network whose input layer would simply take the raw pixel values from this number and plug them in as the input neurons of a neural network. So this neural network would have 784 neurons in the input layer. And it has 784 because it has 784 pixels, 28 by 28, right? So something like this, right? We'll take this number of a 9, we'll plug all of the pixels into these input neurons. There's 784 of them. And then let's say we have a 2-layer neural network. We'll have 15 neurons in the hidden layer. And what we'll do is, if we wanted to classify the digits, what we'll do is we'll have 10 output neurons, one corresponding to each digit. So this is the neuron for a 0, there's a neuron for a 1, for a 2, and so on. And we'll feed it through, and we'll observe the values that it gives us. And then we will we'll classify it as the number corresponding to the neuron who has the highest output value. Right? So this 9, we plug in these pixels, we do a forward pass through the network, it gets multiplied by all these weights, and we get values here. Then it gets multiplied by these more weights, and we get values here. And whichever one has the biggest, we know that it's that number. And we hope that it looks like this, right? We hope that when we have this 9, that we get an image of a 9, the 9 neuron will have a very high value. It's in green because it's a 9. We know that it's a 9. And the other ones will have low values. So you see red bars here. They're kind of small. We hope that, right? But in the beginning, when we just set up the neural network, we don't know what the weights should be for that to happen. The weights will all be random, so we'll have random behavior. And it's the process of training the neural network in which we have an algorithm figure out what the correct weights should be. And I should say that's a little misleading because there are many different combinations of weights that might work. But so we want to find a set of weights which does okay. Like maybe it's not the best set of weights, but it's a good set of weights. And that's going to be the process of learning. So, okay. Mm-hmm. Yep. Exactly. Yeah. Well, but of course, you want more than just 4s. You want to train it on all of the numbers. Yeah. Yeah. All right, that's right. So these are just a few examples, right? The 9, a 2 should give us something like this. And you see that like the weights are such that it thought maybe it was a 3, just a little bit. So, this has some properties of a 3. Like you can see that this is kind of a 3-ish. And so that's typical. There will be some confusion, but we wanted to get the correct answers, right? Okay, so let me stop this. Okay. So let's look at an example of the training process. Now, before I tell you how the weights are figured out, I'm going to show you an animation of the weights actually being figured out. We'll talk about how training is done in a second, but first let me show you a little bit of visualization. So suppose we create a neural network which has one layer. So we just go directly from the inputs, our pixels, to the outputs, our 10 neurons corresponding to these digits. We can do a visualization, which I actually now finally have some visuals which will make it a little easier to construct. Let me go into here. This is one of the chapters. Okay, so suppose we make a neural network that I just showed you this, right? It's a one-layer neural network that takes our pixels here and goes to these 10 digits that correspond to the digits, right? You see all these to-dos, so everything's not done yet, right? Now, let's focus on one of the neurons, right? Every one of these output neurons has all of the pixels plugging into it as connections, right? So the 784, these pixels, all of these, we kind of take these, they're in the image, they're like it's a square, but we kind of unwrap it. We unroll it into this big long column of pixels, of pixels inputs, right? And those pixels all have connections that plug into this output neuron, right? And we can see one of them right now. There's 784 weights on these connections corresponding to these pixels, right? So instead of visualizing it this way, which you're looking at right, like over here, right here, instead of visualizing it like that, let's visualize it like this, right? This neuron right here, the Z, corresponds to this, right, or this. And the way it's shaped is that all of these images, the images are squares, right? So here are pixels, x1, x2, x3, all the way to x28, and then all the way down until we get to x784. So each of these has a weight that you can visualize in the same grid form, right? Instead of having them all as like these connections, we can have them arranged as a grid. And so the way this is calculated is it's Z, the Z is basically x1 times w1 plus x2 times w2 plus x3 times w3 and so on. And then they all get summed together. So it's the sum of all of these. It's the weighted sum plus b, which you can ignore. Basically, just forget about it. It's not important for us. For a scientist, it's important, but for us, it's not. So that's the main thing, right? So let's visualize. So we can visualize the weights, right? We can color them so that whatever the lowest values are, we'll color them black, and the highest values will color white, right? And so if we do that, and we train it, and we start to feed it lots and lots of examples of digits, it will learn a set of weights. I won't tell you how just yet, and not even in that much detail anyway, but we'll see them being learned. And at first they're random, so these are the visualizations for each one of these, right? So this is the visualization of the weights plugging into this neuron. This is the visualization of the weights plugging into this neuron. This is for a 0, this is for a 1, this is for a 2, and so on, right? So if we start to give it examples, it starts to adjust the weights, and slowly this happens. And you see what's happening here? It appears to be, we're seeing something that looks like the numbers themselves, right? So you see like this looks kind of like a 0, this looks like a 1, 2, 3, 4, 5, 6, 7, 8, 9, right? You guys can kind of see that. Maybe if you squint your eyes a little bit, it might become more apparent. We can actually go back and look at all of these. So they look like this, right? Why is this happening? Or why would it be good for the weights to look like this? Does anyone want to like take a guess, like make a guess as to why something like this should happen? Anybody? Yeah? Have you? Right. So what we want is like let's go back to the demo. If you look at these weights, right? They're being multiplied by pixels that come from these images, and we want this neuron to have a high value when it receives zeros. Zeros tend to have pixels on around here, like where I'm circling the mouse, right? Roughly around there. And so we want it to have high weights so that you get high weights times high pixel values to get high scores, right? And so that's why this is white around here. The 1 is white around where 1s happen to be, and white around where 2s happen to be, and so on. Because we want big numbers times big numbers, right? We also want to have low weights for pixels which are usually in other numbers, but not in ones, right? Because we want it to be that when we get a 1, for example, we don't want this to be too high because 1s tend to be high here. You know, they kind of appear in the middle. And so if these weights were high, then 1s would give this a high value. And we don't want that. We want it to have only a high value for zeros and a low value for other numbers. So for pixels that tend to be on in other numbers, we have low weights. High weights for pixels that tend to be high in zeros, low weights for pixels that tend to be on in other numbers but not zeros. And that's true for all of these, right? So the white happens to be where pixels tend to be high. And that's why it looks like the numbers themselves, right? You get these sort of, it looks almost like an average of the numbers. Does that make sense? Kind of, right? So this is kind of neat, right? Because our algorithm doesn't know anything about the numbers themselves. It's just images to it, you know, pixels. But it's creating something which appears to us like as though it's a hallucination of the class. You know, like it's imagining what a 0 looks like, what a 1 looks like, what a 2 looks like. And this is really the first place where we observe something which is really special about these. They're kind of learning what these things look like. And that'll be important when we get into like these sort of generative techniques, which use this information to create new instances, right, of these things that it's detecting. So that's the training process. And these are the weights, what they look like, right? I'll mention really briefly. So one of the things about we're not actually going to talk so much about the learning algorithms themselves because for them it's a bit out of the scope. It's quite interesting. It is the like central sort of research problem that exists in machine learning, and I'm gonna kind of do a cheap version of it right now and just give you like a very, very high level explanation of how training works. It's beyond the scope of what we're doing because it's like we're kind of more concerned with neural networks already as they are trained, and we have we have software which efficiently does train it for us. But it is useful to know it, understand it in some sense. So the way it works is kind of like this. Like we start with random weights, like this, and then as we feed it samples, what happens is we send it, right now, the way it is if we have random weights, if we send this value of a 5, all of these will have like a random outputs, right? More or less random, sorry. Random outputs. And we want the 5 neuron to be high and the other ones to be low. So what we can do is we can actually use calculus to figure out the slope of our accuracy function, like a loss function, which is like how inaccurate our model is. We take this function of like that measures the loss with respect to the weights, and we take its slope, like in calculus, right? You can take the derivative, and then you basically change the weights to move against the slope, to like go down the slope, so the loss gets lower. I know that may seem like if you're not used to calculus, that may seem like magic or whatever and you can think of it as magic because it basically is. But it's kind of like, suppose we have a function, we're looking at a function which plots our loss, our accuracy, with respect to the variables that we're changing, right? We can see it. It's like a function, and it might be shaped kind of like a bowl almost, if in multiple dimensional space. Like if you have it in one dimension, it's like most people here have probably taken one-dimensional calculus, right? You have a function. We want to go down. We want to get the lowest value of the function with respect to the variable, and so we can use calculus to arrive at that, right? And this is kind of like what you learn in first semester calculus. You know, saddle points and local minimums and all this kind of stuff. You kind of go down. That's what we want to try to find, because our function is the loss. Loss being sort of the opposite of accuracy. We have a high loss if we have a low accuracy. But really we actually have 784 variables. So our loss is not actually a one-dimensional graph. It's a 784-dimensional graph. So it's very, very many dimensions, so we can't really visualize it. So it's basically like a hyperbole. A hyperbole means it's a bowl it's like bowl-shaped in a very high-dimensional space. And we are using calculus to kind of descend down this bowl until we find the lowest point of it. And that happens at a certain combination of the weights, which gives us the lowest, not the lowest possible point, but a low point. That's training. It's called stochastic gradient, or it's called gradient descent, and it's the way that we solve. And it's not just for neural networks. It's actually, this is basically optimization with multiple dimension, multivariable functions. This is how they are solved. So this is actually commonly found in many of the sciences and economics and things like that. So that's how neural networks are trained. You can spend like a PhD learning about all the ins and outs of this, and I just described it for you in like 10 seconds. There is, for those of you who like have a little bit more of the mathematical background or are interested in seeing a bit more about this, I am writing a chapter in the book about it. It's not done yet, but there are lots of resources that show you, that describe it a little bit more elegantly with visuals. It's not as bad as it sounds, but that's more or less the process. The thing that the practical consideration for us is that in training, the way it works is that it does these sort of small updates to the weights. So we get a sample or maybe a few samples, and we figure out how to change the weights just a little bit to make the loss just a little bit lower. So it's a sort of iterative process. So as we give it more samples, the weights change slowly, and the accuracy goes up. And that's what happens. And we find the values of these weights that work for our function. And from here on, we can refer to this as magic. It's basically magic. We have these software algorithms which we set up our neural network to have the structure that we want and to take in the data that we want. We give it data and we give it output values. And like magic, it will figure out the weights that satisfy our function or satisfy our data set. And that's more or less how practical machine learning works. A lot of this, today we'll actually be constructing these with Wekinator, but a lot of the stuff in deep learning, we're actually just going to be using pre-trained neural networks. Like you can download neural networks, the weights for neural networks, which have been already trained by people before. So this is kind of like something to look forward to, because we have these really powerful neural networks which were trained by experts using a lot of expensive machinery, going for a few weeks at a time, and now we can use them for various purposes. So that's kind of a nice thing. Okay, so just like before we break, I'll just kind of like zoom out and talk about the big picture of this. So the idea is that like neural networks take data and they map it to another sort of representation of that data, right? So in this case, we're mapping pixels to digits, right? In another case, we might be mapping atmospheric conditions to amount of rain, right? The idea is that we're mapping. We're creating a functional map between one sort of input data and some corresponding output data. So if you think of it that way, you can think of it in a much more general way, right? So we like the examples that I just gave you are used for prediction and categorization, sort of like analytical tasks like that. But they can be used in other ways as well. They can be used, for example, to compress information from low dimension from sort of like a very high dimensional input space to a lower dimensional space, which can carry more information, like a density of information about that characterizes that. We'll be talking about that later. And the thing that we'll be doing kind of today is mapping events to actions in like a media art context. So if you're a media artist, you might commonly have a use case where you have some input data from a camera, let's say, and you want to have that trigger actions, depending on what the camera sees. So that can be accomplished with a neural network. We have a learning algorithm learn the correspondence between the input data that it sees, the pixels of the camera, and the output data that you want it to do. So some trigger or some sound or some action, right? And that's kind of like something which we can use neural networks for, and which is what we'll kind of do in the afternoon. And we'll talk about this kind of more complex stuff later. But in the afternoon, we'll show how to apply this for basically real-time machine learning to connect input actions to output actions. And that'll be using something called Wackonator. And I guess like maybe at this point, yeah, I think we can kind of close up for the morning. So in the afternoon, we're gonna now put these ideas into practice with software. And yeah, so why don't we just go ahead and take a break now? And when we get back from lunch, we can actually try this stuff out. Yeah, okay, cool. Also, just before we break, I just want to quickly ask, I'll stop this here.